In this video, we will discuss augmentation and regularization, and for this you will need two notebooks. This second one on regularization is a copy of the MLP exercise from the first week, specifically the L2 regularization exercise from the bottom of that notebook. Hence, if you've already completed that, then there's nothing more to do. So starting with regularization, as we've seen previously, the problem with offering a machine learning method to many parameters is that it will learn to overfit to the noise in the training set, and as a result perform poorly on validation and test data. There are several different ways of implementing regularization in neural networks. One option is to penalize the network by adding a penalty term to the loss, for example through L1 or L2 regularization. Here, L1 adds a regularization based on the absolute value of the weights, and for L2, regularization is based on the square of the weights with the factor of a half designed to make the gradient cleaner. In this way, L2 will heavily penalize large weight amplitudes to prefer a spread of small weights across all available parameters. In this way, it will encourage the network to use all of its input a little rather than some of its inputs a lot. L1, on the other hand, will enforce sparsity, pushing many weights very close to or exactly to zero, effectively reducing the total number of parameters learnt. Based on observations of better performance, L2 tends to be used more regularly. Other options are to implement dropout, which will encourage the network not to memorize, although, as we saw previously, this has fallen out of favour because it doesn't seem to play well with batch norm. Probably something to evaluate for yourself though. Finally, weight decay is something that we previously saw as an option when looking at the PyTorch optimizers. The idea here is for each update to multiply weights by a factor slightly less than 1 to prevent them from growing too large, thus with a very similar impact to L2. So in our tutorial, we will go through adding L2 regularization to our MLP implementation. You may optionally choose to also try L1. Next, let's look at augmentation. So the idea is simple. The goal is to apply transformations of our images to simulate the appearance of more data and help our network become robust enough to spot the same object located in different parts of an image or far away or close up. Or perhaps with medical images especially, we might want to simulate changes in shape, appearance or noise. So to do this, we can simulate the effect of seeing an object in different parts of an image through translations. We can simulate changes in scale through crops with resampling, and simulate changes in pose or shape through rotations, scales, flips, or affine or elastic deformations. At the same time, we can simulate and add random noise distributions or take noise away through smoothing. We can also change contrast or simulate artifacts. The key, however, is to choose augmentations which are realistic in terms of the types of variation we expect to observe in our training and, more importantly, test sets. We want to help the network generalize. In other words, don't choose a transformation that generates images that you don't expect to see. For example, organs moved to the wrong part of the body or deformed in ways that change it beyond recognition. So to see how these types of augmentation might be implemented, let's revise geometrical transformations, starting with linear ones. So a linear transformation is one which may be implemented as a matrix operation. So here M is our transformation and X is our original data. So in order to apply a flip, all we need to do is invert one or more of our axes. So this equates to implementing M as a multiple of the identity matrix with -1s corresponding to the axes you wish to flip. So in this case, it's the first or the x-axis. On the other hand, rotation by angle theta requires rotation matrices with entries corresponding to cos or sine of theta. In practical terms, these can be implemented just using the SciPy ND image rotate function, which both rotates and then resamples the result back down onto a regular image grid. So next, stretches the scales along major axes. So again, the transformation is in the form of a diagonal matrix where the entries will be greater than 1 for the axes that you want to stretch. So in this particular example where we're stretching along the x-axis, Sx will be greater than 1, but Sy will stay as 1. Shears, on the other hand, add off-diagonal terms to the stretch. This ensures that the stretch is scaled relative to the position along the other axis. For example, this square is stretched up for negative x and down for positive x. So each of these are individual rigid operations, but if we wanted to, we could combine them and add a translation. By adding a translation, it technically means it's no longer a linear transformation, as we cannot represent this by a single 2D matrix, but we can compose this as a matrix operation using homogeneous coordinates, where to do this we extend the two-dimensional, in this case anyway, coordinate vector to 3 dimensions by adding a 1 at the end, and then we multiply this with a 3 by 3 affine transformation matrix, where the translation forms the final column. However, again, you don't really need to worry about implementing this from scratch because there's a SciPy function that will do it for you. So the last geometrical transformation we will look at would be nonlinear transformations. So these essentially assume that each point in space may transform by a different displacement. However, if you actually implemented it this way, giving every single point in space a different random transformation, it would result in a mess. It would turn the image to noise. Therefore, what is done in practice is that a displacement is learnt for a lower resolution control point grid, which is then used to regularize the solution, same as is used for non-rigid image registration with free-form deformations. So the idea is that this coarse control point grid is placed over the image, and then random displacements are added to each of the control points only. The displacements of these intermediate data points of the image grid, shown in blue, are then estimated through a weighted sum of the displacements of the closest control points, where the weighting is controlled through B-spline interpolation. So in more detail, the idea is we take this coarse control point grid, noting that the degree of deformation is going to be inherently linked to this. The higher resolution we go with our control point grid, the more fine-grained and less smooth the resulting deformation will be. Noting very importantly that since the random deformation is learnt by applying completely random displacement vectors to each of these control points, with nothing constraining these to be biologically plausible, neighbouring ones can easily end up pointing in completely different directions, and this is going to stretch the image in strange ways. So it's probably best to implement something fairly coarse. So then the B-spline interpolation stands to smooth in addition to the regularization of this coarse control point grid. The idea is that it's used to project the coarse scale warp estimated by the control point grid to this underlying high resolution image grid, where the displacements of each individual point in the original image grid will be estimated as a weighted sum of the control point displacements, making the assumption that this coarse grid is actually a set of splines, or piecewise polynomials, parameterized by the control points. So B-spline interpolation over 3 different orders are shown in these images that are borrowed from an ITK presentation. The order of the interpolation is going to control how many orders of separation separate the point of interest and the control points that contribute to its displacements. So in other words, if we use a third order B-spline, control points up to 3 grid points away will add to the weight of the averaging. Higher order B-splines will therefore automatically be smoother but more costly to compute. And we'll ask you to have a go at implementing these augmentations, specifically the flips, rotations, and the B-spline elastic deformations in Thursday's tutorial. So let's now move on to options which modulate the intensity distributions in the image. The first thing we might want to do is simulate noise, as this may make the network more robust to noisy unseen images, and as we saw previously, we might observe different noise patterns on different scanners. So if we want our model to generalize to data collected across multiple sites, perhaps this is something that we would want to do. The way that we add noise depends on the scan. For example, CT images exhibit Gaussian distributed noise, however, MR images exhibit Riccian distributed noise. This is because the MR signal is actually collected in the Fourier domain before it is Fourier transformed to generate the final image. So if we assume, therefore, that the noise of the collected data was Gaussian, then we must simulate noise in an MRI image as Riccian, as the Fourier transform of a Gaussian distribution generates a Riccian distribution. And again, we'll implement this Riccian noise simulation in the tutorial. The next thing we might consider is bias. So bias is a problem in MRI imaging caused by inhomogeneities from the applied B1 radio frequency field, which is used to excite the hydrogen protons in tissues during imaging. So these inhomogeneities disproportionately impact the centre of K-space and so end up adding low spatial frequency modulations to the data. In a similar way to B-spline modelling of deformations, therefore, we can simulate this coarse scale modulation through a weighted sum of low-order polynomials up to order n, where n is equal to the dimensionality of the image. Therefore, for 2D, you would implement the following, summing up to 2 each time, where the coefficients C, K, L here are randomly generated, and the bias field itself is multiplicative. So we're going to implement this bias augmentation for you in the notebook, but it would pay to go through it and check that you know what each line of the code is doing. So in summary, augmentation helps simulate the appearance of much larger datasets. And while we've gone through some common types of augmentation that you might commonly consider using, the list is far from exhaustive. Just make sure whichever augmentation you use, it makes sense for your data. For example, I work with the brain, so if we think about the brain, we know it's loosely left-right symmetric and we have common structures on each hemisphere. So it does make sense to mirror flip brain images from left to right, as then your right hippocampus might double up as simulating a left hippocampus, and the same for all other brain structures. On the other hand, you're rarely going to get a brain image upside down. Rigid and affine transformations, however, are reasonable, so you'll often see that people don't place their head in the same orientation as the scanner, and that brains are different shapes. So rotations, translations, scales, affine transformations are all reasonable augmentations to apply unless you pre-processed your data by spatially normalizing it to remove this variation in the first place, in which case what's the point in additionally simulating it? Nonlinear deformations also can be very helpful, however, do be careful with how you apply it. So the original implementations were based on random displacements with Gaussian smoothing, and this is what you get in many commonly available toolboxes. This actually makes the parameterization really temperamental. You don't have to push the smoothing sigma down much, or the size of the random displacements up by much, before the results become highly pixelated. And finally, before I finish this section, I just want to recap the concept of adding augmentations to custom datasets. So in this week's tutorial, we're going to show you how to perform augmentations themselves, but to use them with a PyTorch dataset, it can be useful to wrap them up into class objects. Then there's no need to pass the parameters of the operation each time, and you can easily compose them together. So this is the example from the official PyTorch tutorial, which gives an example of what one of these classes might look like. So you're using a basic Python class structure where the bare minimum that you're going to require is to overload the call method with the specific operations of the transform. And if you want to say specific parameters to use each time, then you define them in the constructor. The custom transformation can then be applied by creating an instance of this class and then passing a sample from your dataset to it. So you could just pass a transform object to your dataset, but often what you are going to want to do is apply a series of augmentations to your data one after another. So to do that, you may want to make use of the Torch Vision transforms.compose method that you can import in this way. And then you can put together several different transforms by passing them to this compose method as a list. And then this is just an example of passing that object to the transforms argument of a custom dataset class. So that's it now for augmentations, and in the final lecture we will go through patch-based training and variance to batch norm.